In the 60s, it was relay-based. Install where the need was recognized. So based on your experience, you decide, oh, we've got an issue with pressure, you put a high-pressure trip in using relays, hard-wired trips and interlocks. Now, these still exist. There are plants out there 40 to 50 years old, and they haven't made any changes. These relays are still there. They still work. Relays are reliable once you sorted them out, once you look after them, keep the dust off them. You can still use them. You don't have to put in programmable systems. You can still use relays. Okay. But that's where we started with relays. The 70s, first solid state logic came out. The Bailey system was one of the first. And a lot of nuclear power stations, the Bailey system is still the safety system. The earlier generation nuclear power stations. The ones that are being decommissioned have these boards in them. In the 80s, the first PLCs appeared. I'm showing my age when I say that I was around when they did appear. We started using the Omron PLCs. Okay. And they started to replace solid state and relay-based systems. They are flexible, they're programmable, the changes are made easily. The cost to implement is a lot lower than building a relay panel. It doesn't take time. So there's a huge benefit to using these from a cost point of view. Okay. But there were no standards for safe software, because people would just program assuming it's correct. Okay. The hazard risk analysis procedures were developed in the 80s. So one of them came out of ICI, they started developing hazard PHA processes. The American military developed some of the hazard methodologies for the development of the Abrams tank. So during this time, these procedures were developed, a structured way of analyzing hazards. The 90s, the first safety PLCs came out, the functional safety controllers appeared. Keener and Honeywell. Well, this system was originally designed by Pepper and Fuchs. It was bought by Honeywell, and there are still systems running now. A lot of them are being phased out now because they've reached end of life, but there are still systems out there running. Okay. Standards for PLCs are developed, the 61511, I think it is. Okay. Development of quantitative risk analysis, that's the FAST type analyses. The dispersion analysis, explosion analysis, overpressure analysis, all those type of analyses were developed. Software was developed, the techniques were developed. Okay. And a systematic approach for risk identification was developed. The lifecycle approach. You start this way and you do it this way. You don't do it any other way. So we're trying to address the specification changes, the people were issues. Keep that in mind. During all of this development, the accident rate did not come down. Even though we thought it's new technology, it must be better. The accident rate kept climbing. It did not show any sign of coming down. It kept climbing. It's because of this, the people were issue. It's all very nice to use a Honeywell FSC because it's got flashing lights and it's great. We can program it and we can make changes. We can make a change today. We can make another change tomorrow. Great. But we're not addressing the people where problems. Are we introducing dangers? Are we introducing problems? In the 2000s, we started to see the first certified equipment, field equipment coming out. The safety PLCs came first, then came the field equipment. People started to see that it's not just the logic solver that must be certified, it's the transmitters, the valves, the field equipment. These started to be certified. 2003 was the first release of 61511. And it was only then that 61511 was released. 61508 was released in 1998, 2000. You can see that a lot of these safety PLCs and techniques were happening before the functional safety standard. And it was because of this increase in accident rate that they introduced these standards. Modern transmitters, modern PLCs come with better diagnostics. They're built into them. They self-test. They provide this benefit of being able to tell you, I've got a problem, please fix it. The safety lifecycle process was developed. That came as part of the 61508 and the 61511 life cycles in the standard itself. 2010 has been an absolute explosion in certification projects that we're doing now. It's our biggest source of income for exiida, certification project. And we're certifying all sorts of things now. We've introduced now, we're busy developing a program for integrated final element. When you buy a ball valve, you buy I'll use manufacturer's names, you might use a Cameron ball valve with a rotor actuator and an ASCO solenoid. So you're putting 3 certified devices together. Who says you've done the right torque calculation, the right timing calculation? So we're putting together to certify that entire assembly now. Okay, so it's gone beyond the devices now. We're going into sub-assemblies, certification. We're trying to eliminate these people-aware problems, addressing that now at a subsystem level. The reason is because the failure rate for those subsystems, we expected it to come down by the use of these certified products. We saw a trend, we saw it still rising. There were still accidents involved that were happening because of failures of these devices. And because of the design process, the people problem. So, I've stressed the people problem. So now, you as managers, I'm trying to explain to you now, how do you address this? Either an operating plant or an engineering plant, a company, how do you address this? How do you eliminate those people-aware problems? Well, following best practice, the standard gives very good guidance. The equipment gives very good guidance on how to manage this. Okay? You do it through a life cycle. You do it through a structured way of doing work, a workflow that is predefined. It suggests the workflow. You as a company can set your own up, which should follow that. If you want to be compliant, you use this, but you've got to follow the concepts defined in this life cycle. So you've got a concept, and we talk about a greenfield project, concept, feed, design, test, install, and then operate, and change, decommission. So you're managing it. Now that's the workflow. Now on the slide, you'll see there are 3 blocks. And that is the management of functional safety. We're trying to find errors that have crept in, people with errors that have crept in executing this work. We're trying to find them and eliminate them early before they progress further in the life cycle. So we stick into place management of functional safety. You manage each phase of the life cycle by nominating people to do certain things. You get people to check certain things. You get people to do at certain stages independent assessments. How are you doing so far? Okay, what they call functional safety assessments, and there are 5 defined in the standard. 2 of them are mandatory. You have to do them. That is number 3, which is right before the hazards are present, and number 4, you have to be doing regular audits after modifications. However, if you look at the requirements for number 3, the first step, the first question is, make sure that number 1 and number 2 are done. If they're not done, do them. So the problem comes, and I've often been called to site, please come and do an FSA 3. We're waiting to start. Our pre-startup safety review is saying, quickly do an FSA 3. And we want to start on Monday, and I get called on the Wednesday. So I go to site, open the books, and I say, where's your FSA 1? We haven't done it. Okay, let's start at the top. So 2 weeks later, I'm still going through everything. And they're all very angry with me. And I say, don't be angry at the messenger. You should have been doing this. prescribed this to be done at this stage. Should have told you to do it. Okay. So it is a structured way of managing people, managing your projects. Okay. The objective, as we said before, is to build safer systems that don't have the problems of the past. We know more now than we did 10 years ago. We're learning. So we want to improve. We want to build safer systems. We want to be more cost-effective systems. Build more cost-effective systems that match the design with risk. Okay. We want to eliminate those bad designs, the weak link designs, those ones that have not worked well in the past. We want to make sure they don't propagate through and continue. Either be changed on the plant or not allowed to be used again in designs. Okay. And once again, we want to provide a global framework for consistent designs. That's the key. The consistency. So we're trying to avoid these systematic faults. The overloading of that truck. There was only one thing going to happen with that truck. Okay. It could have been avoided. People made that decision. The truck didn't suddenly start grabbing packets and overloading it. People loaded that truck. Whereas the random hardware failures, we can manage. If we've avoided the systematic faults, we've eliminated the people problem, the errors, we just have to worry about random hardware failures, which happens with equipment. Things break, things wear out. The natural order of things. We've eliminated the people problem, we just have to worry about the hardware problem. And we do that through our mechanical maintenance programs, integrity programs. That's how we manage it. We know about this.